So this question is more related to understanding the geometry of a situation. So I've not put a big kind of blurb and text on here. So this is all more to be explained, and then we can work through how to solve this problem just using geometry. So in this case, the problem would be you've got a light beam that's leaving a block of glass entering air. Just above the surface of glass, parallel to it, is a perfectly reflective mirror. Now we know the angle of incidence that the light beam has when it hits the boundary glass air. And the question is, what is the angle of refraction when the light beam enters glass again the second time around? So if I would sketch this, what you'll have is, here is our boundary between glass and air. Above that, our perfectly reflective mirror. So now what we've got is a light beam. There's our normal that we always need for the construction. That's the incident angle. So that's the case that we have. We know the incident angle as it hits that boundary, and we've got a mirror located there. That could be the scenario that you might be given in a problem. The question is, first of all, can you, in a sketch diagram, sketch how the beam of light will now travel, and then determine under which angle the refracted angle in glass afterwards would be. So light would travel somehow here, enter maybe the glass, and this is the angle that we would be looking for. Let's try to construct this further. So if we're looking at how the beam of light would travel, well, it's going to travel not straight on, it's going to be bent away from the normal. It's going from glass to air, so it might be traveling like that. We know this is the angle R as defined through Snell's law if we would know n. Now the big shout would be, we don't know n, so how can we do any calculations? Because it might be irrelevant. Let's follow through. So it hits now our mirror, which is parallel to here. If we hit the mirror, if you look at your notes, you remember the incoming angle, which is this one, should be identical to the outgoing angle. So these two angles should be the same. Let's see if I can see this is one normal, this is another normal. These two lines are parallel, so we know these two lines are parallel. So if this angle R is measured here, it pops up here again. If we know from the laws of reflection that this angle entering here is the same as it's leaving, so there's air as well. So R as well. So we've got this angle already known. Let's see what happens to the light beam. It now strikes that barrier between air and glass again. Let's sketch our normal again. Okay, so we know this angle between normal and ray, and we've got again a normal and a ray. These two normals, these two lines are parallel, so this is just the interchangeable angle, and this is the angle R that we have. So this angle R is the same here. Now in our scenario, if this is now our light beam that left the glass, entered air, got reflected, and is now hitting the boundary again with the angle R, which is the same as here. So this is exactly the same geometric situation, just the ray of light, beam of light is going in the reverse direction. So it's going in. So in this case, it's going to be not going straight on, but it's going to be bent towards normal. And this angle we can calculate through Snell's law. But it's going to be exactly the same situation because it's the same n, the same r, so it's going to be exactly the same situation. And we know as this light beam leaves this boundary, traveling further into glass, that this angle is going to be identical to this angle. So they're the same. So in this problem, trying to calculate the angle I've just used refracted and incident, even though actually I would have to properly write this angle as being my new angle of incidence, and this angle would be the refracted one. Let's put a little 2 as an index down here. So this would be the proper one as the ray hits the the boundary, this would be the incident angle, this would then be the refracted angle. So we were looking for the refracted angle, trying to keep in line with how I named them at the beginning, and so you can see how they're similar. I left it as R, so you can see the new incident angle is R as it was here, so the new refracted angle is going to be the same as the incident angle over here. So in this case, you've solved the problem without needing to know any kind of actual distances of the mirror. That was irrelevant, or the refractive index. It was just a geometric problem that you solved, knowing how light reflects and how the angles are measured here.